Hello and welcome to this lecture on data representation in the computer. My name is Dr. Ritesh Ujira. In this lecture, we will explore the representation and storage of different data types in the computer. So at the end of this lesson, well, this series of lessons, this being one of 3 lectures on data representation, you should be able to distinguish between analog and digital information, explain data compression and calculate compression ratios, explain the binary formats for negative and floating point rational values. You'll find this very interesting. Describe the characteristics of ASCII and Unicode character sets. Explain the nature of sound and its representation. Explain how RGB values define a color. Discuss the nature of images and raster and vector graphics. And finally, explain temporal and spatial video compression. Now, as I said, in this particular recording, you will learn about complements, which is one of these learning outcomes. In particular, explain the binary formats for negative and floating point rational values. But you will be able to achieve these outcomes by watching the other lecture videos on data representation, which I will post. So let's begin with data and computers, and more importantly, what is the difference between data and information? So we don't want to be too philosophical about this. So let's just say that data is raw values. So it could be some text collected, it could be just numbers, just raw values. And information is these raw values that have been processed. So if you process this data using some structured algorithm or some structured interpretation, then you achieve information. So obviously, like I said, you can be very philosophical about these two concepts, but let's just leave it there for the sake of argument. All right, so computers are multimedia devices. So what do we mean by multimedia? Well, we mean that they can deal with a vast array of information categories. And these include things like numbers, text, audio in the form of signals. You can express images and graphics. So what's the difference between an image and a graphic? Well, images are usually associated with raster, and graphics are usually associated with vector ones. Videos can be expressed it can be expressed, and the system with which these multimedia items are expressed will be the foundational motivation for this lecture. So we will be looking at how do we express these numbers in a computer? How do we express text? How do we express audio? How do we express images? How do we express video? And that's what we're doing here. So it sounds a bit weird, like you didn't have to think about this before. So before, if you're using your cell phone or computer, you would just open up your word processor and type in the letter A, or if you had to do an essay, you type in a whole essay. If you wanted to work with numbers, you could use some of the calculator apps on your device. But here in this lecture, we will be talking about how is that information, how is that data or information actually represented in the computer? All right, so that's the premise here. Okay, and it brings us back to this concept of a bit. So remember from the previous lessons that computers represent everything in binary. All right, and we had this notion of a bit, which is a binary digit. And a bit, being a binary digit, is a variable. It can take the form of a 0 or it can take the form of a 1. So binary, remember, two-valued state can either be a 0 or 1. Okay, we spoke about bytes as well. And a byte is nothing more than 8 bits that are next to each other. So they are contiguous, which means that they are sitting right next to each other. And these bits, if you have 8 of them together, we call them a byte. Okay, so you can think of a byte, as I showed you before, as a little grid like this. Okay, it's a little grid. I'm using my mouse to draw, so please forgive me if things start looking strange. So here it has cells like this. So each one of these cells can take the form of a 0 or 1. So that's going to be, okay, that's 4 bits. Here's 5 bits, 6 bits, 7 bits, and 8 bits. So these 8 bits give us a byte. So I can erase this, and this will be our byte. All right, so 1, 2, 3, 4, 5, 6, 7, 8. And you can populate this with either zeros or ones. And you can't put 2's in here, you can't put 3's in here, only zeros or ones. Here's an example of a byte. All right. Sounds simple enough. So, like I said before in the previous lesson, you get 32-bit machines, 64-bit machines. This just means that in memory, you have contiguous cells like this, but instead of having 8, you'd have 32 cells. You'll have 32 of these little bits sitting next to each other. And this is indexed in memory by an address. So this could be an address. So 6H here is the name of this address. Or if it was 21, this could be the name of this address. But this is implicit, right? I'm writing it out explicitly here, but it would be implicit in memory. This being the explicit part, this being the part that's physically there. All right. Okay, so I'm sure you find this fascinating. I mean, I do. This is very interesting stuff. All right, so that's a 32-bit machine and a 64-bit machine, and these we refer to as the word length. The word length, if I ask you a computer with word length 32, then you should automatically in your mind think about 32 bits sitting next to each other. If I ask you to think about a 4-bit machine, then you should automatically be thinking about 4 bits, not 5, not 6, 4. All right, and you should make sure that the representation of your numbers in this machine follows the word length. So if I say a 4-bit machine, you cannot have 5-bit numbers. If I say a 4-bit machine, you cannot have 6-bit numbers. You cannot have 3-bit numbers. You must make sure that the representation is complete according to the word length. So if I say represent the number 3 using a word length of 4, then what are you going to do? All right, well, let's think about it. I said a word length of 4. So that means that we need to take out all of the other bits. We need to just make sure that they are 4. All right, in every number I represent, if I'm representing the number 3, okay, so 3 would be 1, 1, right? So I have to make sure that I have a 0, 0, 1, 1. This is the number 3 using a word length of 4. All right, that makes sense, right? Okay. If I want to represent the number 2 in a word length of 4, then I just represent it like this. It'll be 0, 0, 1, 0. If I want to represent 1, the number 1, using a word length of 4, then I would represent it like this. Okay, I hope this is clear, because there's a lot of mistakes that occur like this, and I don't want you to make this mistake. It's a very easy one to make. All right, so let's get back to the slides. So one of the outcomes that you found in the list of outcomes is distinguishing between analog and digital information. So what is analog and digital data? Analog data is obtained from the real world. The key word here is the real world, and it is continuous. All right, so observing the brightness from the sun, right? It's physical. It is analog data. The height, your height from babyhood to adulthood is continuous. Your movement through space is continuous. So this is physical, the real world. On the other hand, digital data is represented as a discrete set of states. So digital data, it's discrete. So like I say, it can be in the form of states. So you can have state 1, state 2, state 3, and then all of the values will be, all of the values of the frequency from which is digital data will take the form of these states, so values from these states. So for example, the roll of a dice, this is only 6 states. So it can be a value from these 6 states. A flip of a coin, all right, the result of flipping a coin, that is indeed discrete, all right, because there's 2 states, and the values from these states can either be tails or heads. All right, so analog data can be converted to digital data by sampling. So what does sampling mean? Well, if you have an analog frequency, you can just take every other value from this continuous frequency and save it. And if you do that, you are sampling. So sampling in this way can give rise to digital data. And we can store every other sample in the computer. Obviously, we might not be able to store all of the values in the continuous distribution, but we can store every other one. So we might not be able to store the entire analog data in a computer, right, because of space constraints, but we can store every other point, every other value. And this is known as sampling. So we all know that if we are to store every other value from analog data to discretize it, these values must be stored in binary format. All right, this is important because we already discussed why we use binary format in the representation of values for a computer. But it is important to understand that when we are sampling from analog data to digital data, which is discrete, we are indeed sampling in binary format. Okay. We'll build the intuition for this as we move through this work, but it's important just to keep track of these little flags that I'm sticking in from time to time. Okay, so when dealing with electric signals, there are some important facts that you need to remember. All right, so the first one is an analog signal continuously fluctuates in voltage up and down. All right, you can picture this in your head. Right? The signal moves up and down. A digital signal doesn't fluctuate in this way. It only has high or low states. Well, that's not entirely true. Okay, it can have a number of states. It can have high, low, and medium states. It can have 6 states. All right, so this is not entirely true that it can only have a high or low state. You can have different kinds of states. And it can be corresponding to things other than binary digits, but the important point here is that it is discrete. The digital signal is discrete, which means that it corresponds to form a set of n states, values from these states, all right, in its distribution. All right, that's important. All electronic signals, both analog and digital, degrade as they move down a line. Okay, that's important. The voltage of the signal fluctuates due to environmental factors. All right, so, and these environmental factors is also what cause it to degrade. So when we do degrade, we can get the original shape back by reclocking the signal to get the original shape. We won't go too much into detail about this, but it's important that you know what it means. All right, so if you have a degraded analog or digital signal, you can do a process called reclocking, which allows us to get to the original shape. So in binary representations, we can represent anything. We can represent the lamp on your table as a binary sequence. We can represent anything. We can represent the number of students at Wits University. We can represent the number of students watching this video. We can represent anything. But the data must be represented in binary format. So all you need to do is find out how many objects do you need to represent, all right? And then you can represent that using a number of digits, a number of binary bits. So, for example, let's try to represent the values true and false in binary. Okay, so we need an associated binary string for true and associated binary string for false. So when I say string in this case, I just mean a set of bits together. So for example, true can be represented by 0, 1, and false can be represented by 1, 1. But what is the minimum number of bits that we can use to represent just two things. Okay, so let's think about that. So just to represent two things, I'm trying to open up Paint. All right, okay, so here's Paint. This is how I'm gonna show you how to represent things. So you have one bit. So imagine this is your bit. We want to represent two things. So is one bit enough to represent two things? Well, yes, it is, okay, because you can represent true as with a 1. This can be associated with the word true. And you can represent false with a 0. And that can represent false. All right, this makes sense. Now, all right, so this is the minimum. Now you can represent true with other strings of bits. All right, like I said, you can represent it like this, or you can represent it like this, or you can represent it like this. That's fine. You can represent false also differently. That's fine. But the question I'm asking here is, what is the minimum number of bits? So the minimum number of bits that we need to represent just two things is just one bit, because one bit can take the value of 0 or 1, and that's enough to associate two things, right? So 0 can take false and 1 will take true. Okay, I hope that makes sense. So here we're looking at the minimum number of bits. So remember, the bits aren't these values here. The bits are these boxes. These boxes can take the form of either a 1 or a 0. All right, hope that makes sense. All right, let's look at the next example. So the gears in a car. So when looking at the gears in a car, right, let's see how many gears do we have. All right, let's see. So we can have 1, we can have the second gear, which is 2, then 3, 4, 5, okay? And then reverse. All right, so these are your gears that you, okay, maybe 6 gears in reverse, right? Let's make it one of those fancy cars. Oh, I don't know. All right. So how many objects do we have here? Well, we've got 1, 2, 3, 4, 5, 6, and 7. There's 7 things that we need to represent. So my question then, is 1 bit enough to represent 7 things? Okay, well, with 1 bit, all right, I can represent a 0, I can represent a 1. So that's 2 things. So if it was just 2 objects, 1 and 2, I can represent them with just 1 bit. But if I'm representing 7 things, how many bits do I need? Well, okay, so 1 is clearly not enough. So let's get 2 bits involved, right? So let's have 2 bits. So I now have 2 bits. All right. So in this one, here I can represent 0, 0. That can be one string of zeros or ones. That can represent something. Okay, so that's one object. Then I can also have this to represent another one. Okay, that's 2 objects. I can have this to represent another object. That's 3. And finally, I can have this to represent another object. That's 4. So with 2 bits, I can represent 4 things. All right, so then 4 things. All right, it's still not enough. We need to have more bits. Okay, so let's add another bit. Let's add another bit. All right. So now I've got 3 bits. How many things can I represent with 3 bits? Okay, let's see. So I can have a 0. That's 1. This is one thing I can represent. All right. I could also represent this. Okay, let me write the choices more clearly now, right? So, because it might be getting a bit confusing. So this is one choice. I could have this. I could have this. I could have that. I could have this, 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 and that. So how many choices do I have? Well, it's 1, 2, 3, 4, 5, 6, 7, 8. So I can represent 8 things with 3 bits. So is this enough? Is 3 bits enough to represent the gears of my car? Yes, it is, because I can associate this with gear 1. I can associate this with gear 2. I can associate this string with gear 3. I can associate this next one with gear 4. I can associate the next one with gear 5. I can associate the next one with gear 6. And finally, I can associate the last one with gear R, reverse. Okay, assuming that your car has seven gears. Yeah, fantastic, right? So I've still got one more string that I can represent something with. All right, so it's more than enough, but it's just enough. So the minimum number of bits that I can use to represent the gears of my car, okay, when I got 7 gears, is 3. Okay, let's look at the next one. So numbers. How many bits do I need to represent numbers? Okay, this is now a trick question, right? Because there are infinitely many numbers. Okay, so if there are infinitely many numbers, then how many bits do I need? Well, infinitely many bits. Okay, but unfortunately, our computers can't support infinitely many bits. So I will never be able to represent every number using my computer. Right? It goes without saying. So if you look at the number of bits that are represented by the machine, right, we can have a look at this for C++, right, in particular. So here, how many bits are used in C++ for signed integers? I'll explain what a signed integer is later on the next few slides. But in short, if you've come across shorts in Stephen's course, then a short integer can be represented with 16 bits. All right. So how many numbers can you represent with 16 bits? Now think about that. So if I've got 16 bits, let's go to my paint. All right. So if I've got 16 bits, so here I've got 3. Imagine 16 bits sitting next to each other. How many things can I represent? So with 3 bits, I can represent 8 things. With 4 bits, I can represent 16 things. With 5 bits, and so on, 32, 64, and so on. So how many bits can I use? How many objects can I represent with 16 bits? Okay, because it says here in C++, a short is represented with 16 bits. An integer is 16 bits as well. A long is 32 bits, and a long is 64 bits. All right, so actually an integer here on modern architectures it uses 32 bits. Okay, but think about it. And to help you think about it, I will introduce you to the fundamental counting principle. So the fundamental counting principle says that if you have a certain number of choices, suppose you go into your favorite restaurant to have some lunch, and or maybe not just lunch, you wanna have a whole meal. All right, so you wanna have starters, okay? And your favorite restaurant has starter choice 1, it has starter choice 2, and it has starter choice 3. I don't know if you guys have eaten at Olives and Plates, but the food is just divine. So yeah, so try it out when Wits ever opens again. So you can have main course 1, main course 2, main course 3, and main course 4, right? And then you can have dessert 1 and dessert 2. Suppose there's only 2 desserts. Suppose this is like a really bad restaurant and there's only 2 desserts, all right, because desserts are very important. So if you have 2 desserts, 3 starters, and 4 mains, then how many different combinations of foods can you have? All right, so you could have a possible combination can be something like this. You can have starter 1, main 2, dessert 1. You can have starter 1, main 4, dessert 2. Starter 3, main 2, dessert 1. Starter 3, main 3, dessert 1. Starter 2, main 1, dessert 2. So my question is, how many different combinations can you get? And so the answer is the fundamental counting principle states that all we need to do is multiply 3 by 4 by 2. Okay, because here there are 3 options, there are 4 options, and on the last one there are 2 options. All you've got to do is just multiply that out, and you will get the number of choices that you can have for courses. So if you multiply this out, you're going to get 24. So there are 24 different options here. So how does this relate with what we were just talking about? So, okay, so how does it relate? Good question, right? This is not a digression because I love food. I'm trying to get you to understand how to work out the number of choices if you have certain number of options. I use the food example because I do like food, so I'll put this on the side. And I want you now to look at this and tell me, if I've got 16 bits, so I've got 16 bits. I'm just going to draw very roughly, right? So there are 16 of these. How many different objects can I represent? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13, 14, 15, 16. So let's steal this. Copy, paste. All right. So now we've got 16 different options here. All right. 16 different options for food. How many different objects? So all you got to do in this case, just as we did here before with the fundamental counting principle, is we're going to say there's 2 options for this box, multiply it by 2 options for the next box, multiply it by 2 options for this box, 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 and 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 so on and so on. And we know that there's 16 of these cells. So all we've got to do is say 2 to the power of 16. So it's 2 to the power of 16. And this will give me the number of choices of zeros and ones that I can put in here. So all you got to do is find out what is 2 to the power of 16. And the answer is 65,536. So it's 65,536. This is the answer. So this is how many ways I can arrange zeros and ones in this box. So one way of doing it is this, and so on. All right, you see. So this is what I'm talking about, right? I'm trying to find out how many options do we have. So in this case, it's 65,536. If I added one more box here, what would happen? I multiply again by 2. I doubled. If I add another box, I multiply again by 2, and I double again. So every time you add, because we're dealing with bits, and there's 2 options each. Every time you add, you would be doubling. Okay, so try to think about what would happen if each of these boxes represented 3 things. It was trinary, right? So it's 0, 1, or 2. Then every time you add a new box, what happens? You're multiplying by 3. All right, does that make sense? Great. All right, I hope that makes sense. So this is the fundamental counting principle in a nutshell. That's basically all you need to know about the fundamental counting principle. It's a very, fundamental concept in statistics. So yeah, with numbers, as many as we can afford, but my point of showing you this is that in C++, which is the language that you learned, an integer, you can only represent 65, if there was 16 bits, you can only represent 65,536 different numbers. And you'll find out that that's even less positive numbers in the next few slides. Okay, so the more bits, so now you must be wondering, well, why is it that I can represent more? You might be actually fooling yourself into thinking that you can, because you could be fooling yourself into doing additions with numbers that are greater than this and resulting in overflows, which I'll explain later on. So an overflow, that's so that's when you're adding, going beyond the representation, but it doesn't really work. So okay, so anyways, let's I hope this makes sense for now, because I am gonna explain this more in detail in the next few slides, but as long as it makes sense for now. Okay, great. So grayscale images, how many different bits do we need for that? Well, as many as we like, as long as we have a certain way of representing grayscale images. So let's look at how can we represent grayscale images. Okay, well, here's a suggestion to use 8 bits. All right, if we use 8 bits for grayscale images, then let me delete everything. Okay, so we can have a scale of brightness for different associated values. All right, so we can have 0 indicating very dim, okay? And if we had 8 bits, all right, then how many objects can we represent? Okay, we can represent, so all you would do is you'd say 2 to the power of 8, and that gives you 256. So that means you can represent 256 things. So 0 being the minimum brightness, and 255 being the maximum brightness. All right. So there are in total 256 things that you're representing, okay, because 0 you counted 2. So in total there's 256 things, but the minimum black value would be 0 and the brightest value would be 255. And all of the values in between will be different grays that you get as a result of mixing. So these are different shades of gray. All right. So 1, 2, 3, ... all the way to 255 are just different shades, different grays. So this is now black. This is slightly less black, slightly a little bit more whiter, and so on, where 255 is being completely white. Okay, great. So the last one here is English letters. And the reason I'm going slow in these examples is because I want this really to stick in your head, right? Because this is an important thing to remember. Representing numbers using binary bits is what the game is. It's basically what it's all about. You need to understand how to represent things with binary numbers. And if you understand that, that's what these 3 lectures or 2 lectures are going to be about, depending on how much we can explain in 40 minutes. Okay, so English letters. So let's have a look at English letters. Well, how many letters are there in English? Well, there's 26, I think. There should be 26. Well, let's just double check that. How many letters in English? Okay, in the English alphabet, there are 26 letters. All right, I guessed right. I couldn't remember. So there are 26 letters in the English language. But so that brings us, well, how many different bits do we need? Okay, well, let's think about it. So 26, our target here is to represent 26 things. Okay, but this is actually not entirely correct. So assume that you must assume that you have separate symbols for lowercase and separate symbols for uppercase. So we have 26 lowercase symbols, plus we still need another 26 for uppercase symbols. Okay, so in total we've got 52 different things that we need to represent. So how many bits do we need? Well, let's first explore 2 to the power of 2. So 2 to the power of 2 with 2 bits, if we have 2 bits, then if we have 2 bits, how many things can we represent? Well, we can represent 4 things. If we have 3 bits, how many things can we represent? We can represent 8 things. Okay, so 2 to the power of 3 can represent 8 things. 2 to the power of 4 can represent, okay, so all you're going to do is you're going to work out what is 2 to the power of 4. That's going to give you 16. Okay, 2 to the power of 5 is going to give you 32. Okay, 2 to the power of 6 is going to give you 64. Aha, there we go. So, well, if you are only representing lowercase values, then 5 bits would be sufficient. Okay, so 5 bits would be sufficient, because then you would get 32, and it's greater than 26. So 5 bits would be sufficient. But since you're representing both lowercase and uppercase letters, you need more than than 32. You need 64. So we need 6 bits to represent 64 things, which is enough to represent 52 things. Okay, so that kind of wraps up this, but generally, how many different states can we represent with n bits? Okay, so with n bits, we can represent 2 to the power of n different things. And that's the answer. So, right, with n bits, you can represent 2 to the power of n objects. This is just generalizing, right? Obviously, your n here are these values. Okay, so something interesting that you must have figured out already, because I kind of pointed it out to you, is what happens every time you increase the number of bits by 1. So if you look at what's happening here, here we increase by 1, we get 8, right? So we increase by 1, we get 16. We increase by 1, we get 32. We increase by 1, we get 64. And we increase by 1 again. What is actually happening here? So what's happening here is, so you increase by 1 again, you're going to get 128. But what's happening is we are doubling. All right, so every time, so double 4, you get 8. Double 8, you get 16. Double 16, you get 32. Double 32, you get 64. Double 64, you get 128, right? 256, and so on. So we are doubling. And by doubling, we are actually, well, it goes with increasing the power, right? So think about that also, as I'm planting another flag in here. Every time you increase the number of bits by 1, you are doubling the amount of things you can represent. Okay, so this now brings us to what we call sign magnitude number representation. So the question is, how do we represent numbers? Okay, well, there's different ways of representing numbers. There's the signed magnitude and there's the unsigned magnitude. So in unsigned magnitude, or just unsigned numbers, we are just representing positive numbers only. Okay, from 0 up to whatever number, we're just representing positive numbers. In assigned magnitude representation, we are representing both positive numbers and negative numbers. Now, I refer you back to the example from before where we said, when we looked at C++'s different sizes of the associated bit strings, what we would notice here is that this was for signed integers. So for unsigned, we would use this entire, if it was an unsigned short, we would use this entire 16 bits only for positive numbers, to represent positive numbers. An unsigned integer, we would use these 16 bits to only represent positive numbers. But because it's signed, we would use a half of the 16 bits to represent positive numbers and the other half to represent negative numbers. Now, it sounds confusing when I say it like that, but hopefully after the next few slides, you'll get it. Now, looking at the signed magnitude number representation, signed meaning that we're representing both negative numbers and positive numbers, we need to understand that there's a particular ordering that occurs. Okay, and it might be counterintuitive, but let's try to get through this. So the sign represents the ordering, and the digits represent the magnitude of the number. All right, so your digits here are the magnitude, and the sign represents the ordering. So you got the negative on the left-hand side of the 0, and you got the positive numbers on the right-hand side of the 0. We omit the sign, right? But it's positive 1, positive 2, positive 3, and so on. So when representing negative numbers, let's start with base 10. So we're going to look at all of this in base 2 as well, but let's start with base 10. So using 2 decimal digits, that we only have 2 placeholders. All right, you've got 100 objects to represent numbers, positive and negative numbers. All right, so 100 objects. So let 1 through 49 represent the numbers 1 through 49. Okay, so that's going to be the numbers that represent themselves. And let 50 through 99 represent negative 50 through 1. All right, so this diagram helps you clear it out. So you've got the numbers as you understand them from negative 50 to 49. And these are now the 100 numbers that are representing things. There are 100 numbers representing okay, let's just start to simplify it. 100 numbers at the top here, this row, representing the numbers at the bottom. So for example, 1 is represented by 1, 2 is represented by 2, 3 is represented by 3, 48 is represented by 48, 49 is represented by 49. Negative 50 is represented by 50. Negative 49 is represented by 51. And negative 3 is represented by 97. Negative 2 is represented by 98. And negative 1 is represented by 99. Now, I'm sure your head must be spinning right now. I mean, everything from the last lecture, teaching you about different base systems, I mean, that's enough to confuse a person completely. And now I'm telling you that 99 is equal to negative 1. What is wrong with this person? Okay, so this is how it is. And the reason for this is because remember what we're doing here. We're representing objects with numbers. And these numbers, these associations are nothing more than objects. They are just objects. These numbers that you know and love from primary school, that you learned in primary school, and that you still use today are nothing more than symbols. And these symbols can be represented by numbers, binary numbers in a computer. We'll look at the representation of these symbols as binary numbers. But first, let's first look at these representations in base 10, just to try to help you simplify it. So how do you convert from here to here? Well, if you're given a negative number, all you got to do is subtract that negative number from 100, okay? Because there's 100 things in this representation. So 100 minus 2 is 98, and that gives you the number that the computer understands. So if you want to represent the number negative 3, just say 100 minus 3 is 97, and that's the number. 97 is the number that the computer understands as negative 3. So when you say negative 49, the computer is thinking 51. When you say negative 50, the computer is thinking 50. That's another way of understanding it. But what we are doing here more concretely is we are using numbers to represent negative numbers, and this is an easier way. You'll see later, it's an easier way to do arithmetic as well. Okay, great. So to convert, as I told you before, to convert to the new scheme, just subtract the number you want to make negative. So if you like negative 1, negative 2, and negative 3, you just subtract them from 100 to get these numbers at the top. All right, that's easy. And easy to convert back, just subtract the number in the negative range from 100 as well. And that's also, you can convert back and forth. It's pretty simple. All right, so let's now do arithmetic in this new representation. So just to make things easy, I've got the number line at the top, but you'll find that this is quite simple. And if you just listen to me, you will be able to pick this up very quickly. So to perform addition, add the numbers and discard any carry into the 100th position. Okay, that sounds very hard to understand, so I'm just going to go straight into examples. So 5 is a positive number, so we leave it as it is. All right, positive numbers, we leave them as they are. All right, they're not hurting anyone. They're not hurting our heads. Positive numbers are exactly as they are. Negative numbers, on the other hand, give us headaches. These are the ones that are negative. And if I'm given a negative number, I need to convert it into this signed representation so that I can perform the arithmetic. So 5 stays the way it is. It's positive, going to stay the way it is. Negative 6 is a number at the bottom here. And we need to find out what the number is in the computer's representation. So all we got to do is subtract it from 100 and we get 94. And that's our number. So then we just perform normal arithmetic. So 5 plus 94, okay, is 99. And 99 is negative 1. Ta-da! It works. Okay. Let's do the next one. So negative 4, where is it in the representation? It's here. All right, so how do we get it? All we got to do is just subtract it from 100. So 100 minus 4 is 96. 6 is positive, so we leave it as it is. All right, and then 6 is positive, so we leave it as it is. 2 is the same, so we leave it as it is. And 96 plus 6, right, is 102. But I said in the beginning that there are only 2 placeholders, right? Remember, 2 decimal digits. Okay, the word digit will confuse you. So let's not use the word digit when we're talking about other bases. Let's rather say 2 decimal placeholders. Okay, so even when you write the numbers out like this, it's wrong. It should be 01, 02, 03, 04, 05, 06, 07, 08, 09, and then the rest stays the same. 10, 11, 12, which is already two representations. Okay, so yeah, just to avoid confusion. So you would also write it out as 05 here, 06, just for consistency. And so -4 becomes 96, 6 stays the same, and you get your 102. So we ignore the 100 because we would just copy down the 02. And the reason why we ignore the 100 is because there's only 2 placeholders. So we only keep the rightmost placeholders. So the 02 is kept. So it falls away. All right, it falls away. The -2 is 96. Sorry, -2 is minus 100 is 98. -4 minus 100 is 90. So 100 minus 4 is 96. Just to make sure you get that. 100 minus 6 is 94, and this works. All right, 98 plus 96 is 194, which works. All right, hope this makes sense. And I'd like you to try it out. So try it out. Pause the video and see if you can perform the arithmetic here. So 48 stays the same. -1, okay, the -1 needs to be converted. So we say 100 minus 1 is 99. And then we add 48 plus 99, which gives us 147. The 100th falls away because there's only 2 placeholders. And we stated that earlier. So we end up with 47, and there we go, we're done. Right, so that's the answer, but I'd like you to make up your own examples and try to work it out as well. Okay, let's look at one more, and then we're gonna do this all in binary. So let's look at subtraction. Well, I'd say subtraction is scary, but it's not. You've already done it. You've already done subtraction here. Okay, here's subtraction, here's subtraction, here's subtraction. You just didn't notice it because it looks like it's a separate number, but it's not. It just, this positive here would just be a minus, and then it sinks into this bottom row anyways. So doing subtraction is quite simple. We just have to remember that a minus b is nothing more than a plus minus b. Okay, so -5, okay, minus 3 is -8. So this is a -5. We have to convert it because it's a negative number. This minus 3 is also a negative number. So it needs to be converted to 97. All right, and -8 is converted to 92. If we add it up and ignore this third placeholder, then we get the right answer. Note carefully that this only works if you ignore the third placeholder, right? And that's important. Like I was talking about before, I think if you remember me rambling on about word lengths on this slide, you know, I said that if it's a word length is 4, then it's 4. Make sure you have 4 digits. If your word length is 6, make sure you have 6 digits. This is exactly why I was going on about that, because you actually need it when you're doing this kind of conceptualization, right? Because this 100th position would fall away. All right. So let's try to generalize it if we increase the number of placeholders or the number of digits. So representing negative values, we can come up with a formula to do it. So if you've got a negative value, let's call this negative value I, right? And it's a negative, say that -3, for example, or -4, for example, all right? And you're trying to find out where is it in this timeline, where is it on this number line? Then what you would need to do then is you need to first know the number of digits, the number of placeholders. In this example, there were 2. But you could have 3, you could have 5, you could have 10, you could have 100. You can have any number of them. So that gives you the word length. You remember the word length. So if you have a negative value, negative I, it's equal to 10, because this is base 10 to the power of k, where k is the number of digits, minus I. So before it were 2, so it was 10 to the power of 2, which is 100, and you were just subtracting from 100 to get the different values. But this is a more general way of doing it. So thus, a minus b is nothing more than a plus, this minus b needs to be converted, so it becomes 10 to the power of k minus b, which can be written as 10 to the power of k plus a minus b. All right. And this particular representation is called tens complement. All right, so it's using base 10 to sign integers. This is called tens complement. Now I'd like to introduce you to twos complement. So I hope you understood the last 4 slides, because now we're going to do all of this again, but in binary. Okay. If you didn't understand this, please go back and listen to it one last time before moving on to the next slide. Because in binary, it's the same intuition, everything's the same, it's just the number system that changes. So as a prerequisite for the next few slides, I'd like you to really get acquainted with binary. So try to write down binary numbers on a piece of paper and see how many you can write down. See if you get used to the pattern. And if you know what you're doing in binary. All right, so you just try to get really comfortable with binary addition, binary subtraction, and so on before going on to the next slide. Okay, so let's go to the next slide and let's see how it's done in twos complement. So remember, this was tens complement because it was base 10. Now we're going to be doing exactly the same thing, but in base 2. The intuition is the same, and that's why I introduced tens complement first, because it's more relatable and the intuition now is the same. So in twos complement, we are trying to represent a set of numbers. Here are the numbers we're trying to represent. And we are told that we have a word length of 8. So how many different objects can you represent with 8 bits? So we're asking, what is 2 to the power of 8? And the answer is 256. We can represent 256 things with 8 bits. All right. So how are we going to split this? Well, if we say 256 divided by 2, we get 128. So that means I can have 128 positive numbers and 128 negative numbers. So I'll have 128 positive numbers. I'll include 0 as a positive number. Okay, 128, that's all of these. Okay, it looks like 127, but we remember we're counting 0 as well, so it's 128 positive numbers. And we're then going to have 128 negative numbers. So that's your -1 up to -128. We want to represent this on the number line. So with 8 bits, remember I said if the word length is 8, you're going to write 8 digits down. So 8 bits, you're going to write them all down. So just see, because it's 0, doesn't mean you just write a 0. You're going to write down 0, 0, 0, 0, 0, 0, 0, 0. If you don't write it down like this, it is wrong. Okay, those zeros are not to be omitted. They are part of the solution. Okay, because they are part of the solution, because I'm explicitly telling you that they are 8 bits. That's why you have to write them down. If I didn't specify it, then it's a different story. Okay, so here you have 8 bits, and that corresponds to 8 zeros, which corresponds to 0. 7 zeros and a 1 is 1. That'll be 2. And then 0, 0, 0, 0, 0, 0, 1. 1 would be 3. 0, 0, 0, 0, 0, 1, 0, 0 would be 4. And so on and so on. Going all up to 0, 1, 1, 1, 1, 1, 1, 0, which is 126. And 0 with 7 ones is 127. Okay, so the number that comes after this, okay, right, would be 1, 0, 0, 0, 0, 0, 0, 0. Okay, so that would now correspond to negative 128. Okay, so in other words, 128 does not exist. 129 does not exist. These are beyond the positive number line, and they do not exist in this representation. So to put it bluntly, there is no 128 in two's complement if you have 8 bits. Okay, you can get it if you've got 9 bits. But if you have 8 bits, there is no 128. That number does not exist. The number 129 does not exist. The number 200 does not exist. The number negative 200 does not exist. Negative 129 does not exist. That would go beyond the number line. And we don't have enough strings, binary strings, to represent it. So it goes beyond our number line. So that's important to remember as well. Okay. So if you add 1 to this number, you are not going to get 128. You will in fact get negative 128. That is called an overflow. All right, so stare at this and try to get it, right? It's just the mapping of 8-bit binary digits, binary strings, mapping to numbers that we want to represent. Okay, so now that I hope that's sunk in. So representing negative values, addition and subtraction are the same. And remember we did 10's complement? Well, it's the same. All we got to do is convert the number, and then we just got to do the arithmetic, right? So as you've done before here in these examples, it's the same thing. The arithmetic is the same as you would have done it in 10's complement. So as the same as in 10's complement, arithmetic compute this. Now we are in 2's complement. So the first step is to find out what is 1 to 7 in binary. Okay, so 1 to 7 in binary, well, lucky for us it's over here. 1 to 7 is over here. All right, so 1 to 7 in binary is 1 0 with 7 ones. All right, so let's write it down. Okay, it's going to be 1 0 with 7 ones. That's 1 to 7. Let's write it down. Okay, 1 0 with 7 ones. Oops, let me make this black. 2, 3, 4, 5, 6, 7. I'm not too sure why it's red. I want to make it black. Okay, it doesn't want to go black. Now it's black. All right. So we can make this a bit bigger. Nuts. All right. Let me do it again. So it's 0, 1, 2, 1, 2, 3, 4, 5, 6, 7. Fantastic. So this is now 1 to 7 in binary. So now we want to convert it to negative 1 to 7. So what happened before when we wanted to convert something before? Well, all we did was we subtracted it from 100, okay, or 10 to the power of 2. Here we've got 8 things. So 2 to the power of 8, 2 to the power of 8. If you remember, is 256, and 256 in binary, I'm trying to write this down, is 1 0 0 0 0 0 0 0 0. Okay, this is in binary, 256. That's 2 to the power of 8. Before we had 10 to the power of 2, now we've got 2 to the power of 8 because there's 8 bits. And now we've got to perform the subtraction, okay, just as we did before. So we're going to say 256, which is 2 to the power of 8, minus 127. And that's how we're going to get our negative value. So let's draw a line here, and then we got to compute it. So how do we do it? Well, if you remember, I don't know if you remember how to do this from the previous lesson, but I'm going to try to make this big so you can see it. I hope you can see this. Well, this 1 will go away, okay, because we're borrowing, so we can't perform the subtraction. So we have to borrow. So we go to the neighbor, there's nothing. We go to the neighbor, there's nothing, and so on. So we borrow 2. Okay, and we've got to borrow again. We've got to borrow again. You've got to borrow again. You've got to borrow again. Borrow again. Borrow again. Borrow again. And there we are. So 2 minus 1 is 1. 1 minus 1 is 0. 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 0, 0, 1. Okay? 1 minus 0 is 1. And this falls away. Remember we said that we've got only 8 bits in the representation. So this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now this number 100000001 is negative 127. All right, and that's basically it. So we copy that down here, the 100000001, and you add it to 1, which is 00000001. Okay, remember you have to have that 8 bits. So then you perform the addition. So you add these two numbers together and you get this. And this number is negative 126. And you can check it, it's a negative 126. How would you check it? The same process, okay? If you remember, we said that to convert from, easy to convert to new scheme, just subtract the number you want to make negative from 100. Easy to convert back, just subtract a number in the negative range from 100. Easy, same thing. And you can do the same thing and you'll get back to the original value. Piece of cake. Pretty simple. Okay, but there's a question here. Do you notice something interesting about the leftmost bit? Okay, so the leftmost bit here is a 0. Okay, the leftmost bit here is a 1. Okay, looking at these, 1 to 7, the leftmost bit is a 0. 1 to 6, the leftmost bit is a 0. For 2, it's a 0. For 1, it's a 0. For 0, it's a 0. For negative 1, the leftmost bit is a 1. For negative 2, the leftmost bit is a 1. For negative 1 to 6, the leftmost bit is 1. For negative 1 to 7, it's a 1. And for negative 1 to 8, it's a 1. Well, to me, it looks like when it's negative, the leftmost bit is a 1. When it's positive, the leftmost bit is a 0. So that's something interesting to keep your eye on. And it's designed this way. Okay, so that's fantastic. So that's something interesting about the leftmost bit. And what we did here is we converted a number. Okay, but this looks like a lot of work, right? We converted a number into 2's complement from a negative, right? So we wanted to represent 127 as a negative number, and so we had to subtract it from the binary number 256, and that's how we got this number at the bottom. Okay, so, but this was a lot of work. Look how much of borrowing we did. I mean, that's a lot of work. So we need an easier way to do this. So this is the correct way of doing it, but it would be great if there was an easier way of doing it. So let's try to see if we can work that out. So working out 2's complement as a revisor. For example, for 8 bits, if you want to represent negative x, right, like we did want to represent negative 1 to 7, all we did was we just said 2 to the power of 8, which is 256. In binary, that was 1 with 8 zeros, and we subtracted x from that. Okay, so this is 256 in binary minus x. Well, we could rather write it like this. So we can say if we subtract 1 from this number, then we're going to get this. Okay, then we just have to add the 1 back at the end. So it becomes 8 ones minus the number plus 1. But why did we do that? Okay, well, the reason why is because when we subtract any number from this number, all we're doing is we're flipping the bits. So if you subtract the number from this number, that number its bits flip. And then all we've got to do after that, this flipping bits story, is then just add the 1 that we took out. Okay, I hope that makes sense. And look over the slide again if it doesn't. So the rule then becomes we flip the bits of x and then we add 1. And that'll give us our new number in the negative. So here we went through a lot of trouble subtracting it in this long procedure. But what we can instead do is just take the number 1 to 7, right, which is this. We flip the bits around, so we get 1 0 0 0 0 0 0 1 0. Okay, we flip all the bits. Flipping means wherever you see a 0, you get a 1. Wherever you see a 1, you get a 0. Okay, I'll show you. Let me show you. So the number here is 1 0 with 7 1. So let me write it down. I'll erase all of this. So we get here 1 0 with 7 ones. 1 2 3 4 5 6 7. Okay. So the idea is to flip the bits. So flipping the bits would give us, I'm just going to make an arrow, flipping the bits. So wherever you, remember the rule, wherever you have a 0, put a 1. So you have a 1 now. Okay. So you get this. So this 1, the 0 becomes a 1, the 1 becomes a 0, 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 and so on. And then we add 1. Okay, so then we're going to have, if you add 1 to this number, you're going to get 1, 0, 0, 0, 0, 0, 0, 1, which is the answer. Okay, there you go. That's the answer. Ta-da! Amazing, isn't it? I'm sure now you must be appreciating why binary is so useful. Okay. If you're not, then maybe I can still convince you. So here's another example. So negative 32, it becomes negative, and then 32. This is 32, a positive 32. Okay. Negative 64. Something interesting about this. Do you see something interesting? So do you notice that 2 is 1, 0, 4 is 1, 0, 0, 8 is 1, 0, 0, 0, 16 is 1, 0, 0, 0, 0, 0, 32 is 1, 0, 0, 0, 0, 0, 64 is 1, 0, 0, 0, 0, 0, 0. Can you guess what 127 will be, or 256? Do you see a pattern? If you don't, oh, there is something interesting going on here. You need to look harder. Okay, but anyways, I'll get to that later. So negative 32, this is 32, negative 32. Negative 64, this is a negative put in front of the positive 64. All we do is we flip the bits. So flip the bits. So this becomes 1, 1, 0, 1, 1, 1, 1, 1. That's this number. And then we add 1 to get this number. And this is now negative 32. We have this number. Okay, flip the bits, add 1, and we get this number, which is negative 64. And then we can add it up and we get negative 96. Easy. You can also prove it this way. Here's 96. Flip the bits, add 1, you'll get this number. Okay, hope this makes sense. So, so we spent a lot of time on this, but I hope it's sunk in. There's a lot of interesting things here to appreciate, and it's quite a lot. I understand that it's kind of derailing the way we think about things so far. But I hope you just spend some time to kind of like appreciate how this is useful, how this can be. You can also do some research and try to find out what's going on here, and the benefits of using the binary base as a base 2 as opposed to other bases for doing this kind of problems. I'm sure you also have found out that adding in binary is really simple. Subtracting in binary is really simple, and subtracting now is nothing more than addition, because your subtraction, your negative numbers is already stored as a positive number. Okay, so for example, this negative 96 is stored as a positive number that we can just add. So everything in binary is just addition. Okay, anyway, so there's a lot to appreciate here, but before we finish off now, let's first talk about number overflows. And I've already spoken about this when I spoke about, when I looked at this number line and I asked you about adding numbers to 1 to 7. So if you add 3, for example, to 1 to 7, what you're expecting to get isn't what you're going to get. Okay, if you add 3 to 1 to 7, you must be expecting to get 130, but you're not going to get that. What you might actually get, so you're going to add 3, right? So let's see, you add 1, 2, 3. You're actually going to get the number negative 126. And we all know that 127 plus 3 is not negative 126. It's weird. That's not normal. And the reason for this is because we are trying to map an unbounded world to a bounded machine. That's the big issue here, right? So an unbounded world to a bounded machine. All right. So the number of integers are infinite. We know that. Decanter showed us infinity in numbers. We know that it's infinite, but we're trying to map it to a bounded machine, which means that we have a finite set of memory. And this is what occurs. So here's just an example of how 1 to 7, trying to add 3 to 1 to 7, you're not going to get the answer that you expect. Okay, you're going to be getting a negative, and we can see it's negative because of this. This leftmost bit is a 1. Yeah, and that's basically it from complements. In the next lecture, we'll talk about representing real numbers. So all over here, we've been representing integers in a way. I mean, only integers. Okay, but what happens if we want to represent real numbers like 1.1 or 1.2, 1.3 and so on? Yeah, we'll talk about it in the next lecture. I hope this made sense. Please watch them again and go over it. The best thing about these online lectures is that you can watch them as many times as you like and no one's going to say anything. So watch them as many times as you like. Try to get the concepts, let them sink in. And don't watch it like second-hand smoke, right? Just sit down, pay attention, get some notes, write on a piece of paper as you listen to me speak, and try to like pay attention to what you're watching. Because what I've seen just recently now is students who put this on like music on their iPod, and they're listening to me speak to them while they're gymming, or while they are gardening, or while they are doing all sorts of things where they're not concentrating. Okay, and I have to say that this is what we used to do in lectures, right? So this is serious material, and you wouldn't be listening to a lecture in your garden. You would be normally paying attention, sitting upright at a table, not in front of the TV in your lounge listening to a lecture. You would be sitting upright at a table. You would be having your notes in front of you, a textbook next to you, perhaps some access to the internet available if something gets confusing, and you'd be paying attention in a meaningful way. So my only advice to you is to please watch these lectures not as secondary smoke, but rather take the time to understand what's going on here. All right, I wish you all the best, and I will speak to you in the next lecture.